Hello everybody, my name is Kiran. I am working as an assistant professor in the department of EEE Anits. I welcome you all to my third and final lecture on three-phase circuits. In the first lecture on three-phase circuits, I discussed the analysis as well as tutorial session on three-phase balance circuits. In my second lecture on three-phase circuits, I discussed the analysis and the tutorial session on the three-phase unbalanced circuits. In today's final lecture on three-phase circuits, I am going to discuss the concept of three-phase power measurement using two wattmeter method. According to Blondel's theorem, it states that for measurement of power across n phase balanced system, n minus 1 wattmeters are required. Similarly, for the measurement of power across n phase unbalanced system, n wattmeters are required. Since here analysis is limited to only balanced circuits, according to Blondel's theorem, in order to measure power, that is three-phase power, only 2 wattmeters are sufficient. That we are going to prove in today's lecture. The wattmeter symbolic representation is shown, which consists of two coils. One is current coil indicated as CC and another one is pressure coil indicated as PC. It is a four-terminal device where M stands for mean, L stands for load, C stands for common and V stands for voltage. So there are two possible connections of connecting two wattmeters for the measurement of three-phase power. The first way of connecting is the first wattmeter current coil is connected in R phase and the current coil of second wattmeter is connected to Y phase, and the pressure coil of both wattmeter 1 and wattmeter 2 are connected to the common terminal B phase. Similarly, the second way of connecting two wattmeters, here the current coil of first wattmeter is connected in R phase and the current coil of second wattmeter is connected in B phase. The common terminal of the pressure coils of both wattmeters are connected to Y phase. In today's analysis, we are going to consider the second way of connecting two wattmeters for our measurement of three-phase power using two wattmeters. We know that the apparent power S is equal to V phase into I phase in case of single phase AC, and it is 3 into V phase into I phase in case of three-phase circuits. The active power in case of single phase AC is V into I cos phi, whereas in case of three phase it is 3 VI cos phi. Reactive power in case of single phase is VI sin phi, and in case of three phase it is 3 VI sin phi. Since we are assuming that the load connected is star connection, in star connection we are well aware that the magnitude of line voltage is root 3 times the magnitude of phase voltage, and the magnitude of line current is equal to the magnitude of phase current. So we will get an alternate expression for active power in terms of line values, that is root 3 VL IL cos phi, and reactive power to be root 3 VL IL sin phi. So here, when I consider wattmeter 1, the current coil is connected to R phase, therefore the current flowing in the current coil of first wattmeter is IR. Since the pressure coil is connected between R phase and Y phase, so the voltage across the pressure coil of first wattmeter is VRY. Therefore, the power measurement of first wattmeter can be written as W1 is equal to VRY into IR into cos of the angle between VRY and IR. Similarly, if I consider second wattmeter, the current coil of second wattmeter is connected to B phase and the pressure coil of second wattmeter is connected between B and Y. Therefore, the current flowing through second wattmeter is IB and the voltage across second wattmeter is VBR. Therefore, the power measurement by second wattmeter is given by W2 is equal to VB by IB into cos of the angle between VBY and IB. So now my objective will be to find what is this angle between VRY and IR and VBY and IB, and that can be found by means of phasor diagram. Since it is three-phase balanced load, so here in the analysis of three-phase balanced load, all the three phases, that is phase voltages, will be equally displaced by 120 degrees from each other. That is VRN, VYN and VBN will be equally displaced from each other by 120 degrees. So the first wattmeter reading is VRY into IR into cos of the angle between VRY and IR. So here, since this is assumed to be inductive load, every phase current will lag the respective phase voltage by an angle phi. So therefore IR, IY as well as IB will lag the respective phase voltage by an angle phi. Here, since I want a vector VRY, it can be represented as VRN minus VYN. I already have the vector or phasor VRN, and I also have the phasor VYN. In order to get the vector minus VYN, it is nothing but the mirror image of the phasor VYN. The resultant of these two phasors will give me the line value or the line phasor VRY. So the angle between the line voltage and phase voltage in a three-phase balanced system will always be 30 degrees. Now my objective is to find what is the angle between VRY and IR. So from the phasor diagram, it is obvious that the angle between VRY and IR is 30 plus phi. Therefore, hence I can conclude that the angle between VRY and IR is 30 plus phi. Similarly, from the second wattmeter reading, W2 is VB by IB cos of the angle between them. And VBY can be written as VBN minus VYN. I already have both the vectors, that is VBN and minus VYN. Just finding the resultant of these two phasors will give me the phasor VBY. The angle between the line voltage and phase voltage is 30 degrees, as we are aware of. Therefore, from this phasor diagram, I can conclude that the angle between VBY and IB is 30 minus phi. Since this is a star connected load, we know that VRY and VBY are line values, as well as IR, IB are line values. Since in star it is same as the phase currents. Okay, so I can rewrite the readings of wattmeters W1 and W2. W1 to be VRY IR into cos 30 plus phi, where VRY is line voltage and IR is line current, and the angle between them we have just now derived to be 30 plus phi. Secondly, from wattmeter 2, VBY into IB into cos 30 minus 5, as now we have derived that the angle between these two phase arcs is 30 minus 5, indicating as equations 1 and 2. If I add both the equations, W1 plus W2 will give me VLIL cos 30 plus 5 plus VLIL cos 30 minus 5. If I take VLIL as common, and it is in the form of cos A plus B and cos A minus B. So applying this formula to the above expression, so I'll get the indicated expression VLIL into cos 30 cos 5 minus sin 30 sin 5 plus cos 30 cos 5 plus sin 30 sin 5. Here both the terms will get cancelled. So I'll be left with VLIL into 2 cos 30 cos 5. We know cos 30 is root 3 by 2, which gives me the expression for W1 plus W2 to be root 3 VLIL cos 5. And we are very much aware that root 3 VLIL cos 5 is the expression for three-phase power. So hence I can conclude that in order to measure a three-phase power, only 2 wattmeters are sufficient, and that can be obtained by performing the addition of the 2 wattmeters. Next, from the readings of W1 and W2, if I subtract the equations, I'll get the following expression in which these two terms will cancel each other, that is cos 30 cos 5 minus cos 30 cos 5. So I will be left with W2 minus W1 to be 2 VLIL sin 30 sin 5. Sin 30 is 1 by 2, which will give me W2 minus W1 to be VLIL sin 5. Hence I can conclude that if the difference between 2 wattmeter reading is multiplied by root 3, that is root 3 VLIL sin 5, which indicates the three-phase reactive power. So next, after considering these two equations W1 plus W2 and W2 minus W1, on dividing the equations 3 and 4, these two terms will cancel each other. So from this, tan phi is equal to root 3 into W2 minus W1 by W1 plus W2, which will give me the phase angle phi to be tan inverse of the entire expression. So from this I can derive the expression for power factor cos phi to be cos of tan inverse of root 3 into W2 minus W1 by W1 plus W2. So now considering various cases, first case, if I consider power factor to be unity from the readings of both wattmeter W1 and W2, so W1 will be nothing but VLIL by 2, same is the case of wattmeter 2, and if I add both the values, it will give me the expression of VL into IL. Hence I can conclude that if the power factor is unity, both the readings of wattmeter are equal and positive. Second case, if I consider the angle to be in between 0 and 30 degrees, the wattmeter readings W1 and W2 both will be positive, and the addition of these two wattmeters will also give the positive value. Hence I can conclude that the reading of both wattmeters will be unequal and positive if the angle lies between 0 and 30 degrees. The third case, when I consider the angle between 30 and 60 degrees, both the wattmeter readings will be positive and the sum of the both wattmeters will also be positive. Hence I can conclude that even when the angle is between 30 and 60 degrees, the reading of both wattmeters are unequal and positive. The fourth case, if I consider my phase angle to be 60 degrees, the wattmeter readings, that is first wattmeter reading becomes 0, the second wattmeter reading will have some positive value, and the sum of the wattmeter readings will be nothing but the value of the reading of the second wattmeter. Hence, from this I can conclude that if the angle is 60 degrees, one of the wattmeters reading becomes 0 and the complete three-phase power is read by a single wattmeter. Fifth case, if the angle is in between 60 degrees and 90 degrees, the first wattmeter will become negative, the second wattmeter reading will show positive, and the sum of these two will obviously be positive. Hence I can conclude that is only one of the wattmeters will show negative value if the angle lies between 60 degrees and 90 degrees. In the last case, if the angle is 90 degrees, the first wattmeter will show negative value, the second wattmeter will show positive value, but these two values will be equal in magnitude and only differ in sign. Therefore, if I add those two readings, it will become 0. Hence, I can conclude that the total active power is 0 when the angle is 90 degrees. The advantages of 2 wattmeter method is this is valid for balanced as well as unbalanced loads. Neutral point for star connected load is not essential in order to connect the wattmeters. The delta connected load need not be opened for connecting the wattmeters for power measurement. Only 2 wattmeters are sufficient to measure the total three-phase power, and hence the power factor as well as power can be determined if the load is balanced. The total reactive power can also be determined for balanced loads using this 2 wattmeter method. The disadvantages are it is not applicable for 3-phase 4-wire system, and it should be carefully noted along with the signs of both wattmeters W1 and W2. If proper care is not taken, then it may lead to wrong results. So now we'll discuss some of the tutorials based on the 2 wattmeter method. A 3-phase 100 kilowatt load has a power factor of 0.342. The power is measured by using 2 wattmeter method, and we have to find the reading of each wattmeter if the power factor is leading and lagging. Given the apparent power is 10 kVA, power factor is 0.342. The formula for apparent power, as you know, is √3 VLIL. From this, I'll get the expression for VLIL to be valued to be 5773.5 volt ampere. First, assuming that the power factor is lagging, given that cos phi is 0.342. From that, I'll get the angle to be 70 degrees. We know that the expressions for wattmeter 1 W1 is VLIL cos 30 plus phi, and the second wattmeter VLIL cos 30 minus phi. So on substitution, the values of VLIL and the angle phi will give me the readings of each wattmeter. Now assuming power factor to be leading, so here you can observe that if the power factor is leading, both the readings of wattmeter will get interchanged. That is W1 will be indicated by 30 minus phi and W2 will be indicated by 30 plus phi. So the values remain same. On substituting the values of phi as well as VL into IL will give me the reading of each wattmeter. Next tutorial, two wattmeters A and B are given 5000 and 1000 volts respectively, and he has asked to calculate the power and power factor in two cases. That is, when both readings read direct, and second, when the latter is reversed. So if the circuit voltage is 400, he has asked us to find the value of capacitance which must be introduced in each phase so that the entire power is appearing only on wattmeter A. Frequency should be taken as 50 Hertz. So if it is direct reading, given that W1 is 5000 watts and W2 is 1000 watts, we know the formula that power is equal to sum of two wattmeters, which will be 6000 watts in this case. The power factor, we know the expression for power factor since we know the readings of W1 and W2. On substituting the values, give me the power factor to be 0.65. Now the second case, if one of the latter meters are reversed, so W1 is taken as 5000 and the second wattmeter is assumed to be minus 1000 watts as one of the meters is reversed. So on addition of both the wattmeters will give me total power to be 4000 watts in this case. So on substituting the values of both wattmeters in the expression of power factor will give me 0.36. Here the circuit voltage is given as 400, so VL is 400. So power factor I have obtained as 0.65. So before if I connecting capacitor in each phase, let us see the analysis before capacitor is connected. The total wattmeter reading will be 6000 watts. We know the expression for active power is root 3 VL IL cos phi. So substituting this, we'll get the expression for line current IL to be 13.32 amps. So here the load connected is not mentioned, so we'll assume both delta as well as star. First we'll assume that the load is delta. So in delta connection, the magnitude of line voltage is equal to the magnitude of phase voltage, and the magnitude of line current is root 3 times the magnitude of phase current. So I phase will be IL by root 3. We know the IL value to be 13.32. So will give me the value of phase current to be 7.69 amps. So next the phase impedance is nothing but the ratio of phase voltage by phase current. Phase voltage is nothing but 400 volts. Since the load is assumed to be delta, we know the magnitude of line voltage and phase voltage are same, and we obtain phase current to be 7.69, which will give me the phase impedance to be 52 ohms. Power factor cos phi can be given as R by Z. From this, I'll get the value of R to be 33.8 ohms. So X reactance will be nothing but Z sin phi. We know the value of Z. So from that, I can calculate the reactance value, which is nothing but 39.5 ohms. After including capacitor in the circuit, the condition here that the whole of the power should appear on only one wattmeter. That is, one of the wattmeters should become zero. As we have seen in one of the cases, that is only possible when the phase angle is 60 degrees. So the resistance value will remain same. Let us assume the new reactance to be X phase dash You know the formula tan phi is equal to x by r. From that, I calculate the new reactance value to be 58.54 ohms. So therefore, from this, if I subtract the new reactance value and from the old value, will give me the reactance of the capacitor that we have introduced in each phase, and in this case it is 24.74 ohms. From that, the capacitor value that we have included can be calculated and obtained in this case to be 128.66 microfarads. Now assuming the load is star connected, before connecting capacitor, VL is 400, cos phi is 0.65, the active power value is 6000 watts, and this the line current is nothing but 13.32 amps. Since this is a star connected load, the magnitude of line current as well as phase current is same. The phase voltage is 1 by root 3 times the magnitude of line voltage. So it is obtained as 230.94 volts in this case. Z impedance is the ratio of V phase by I phase. So as on substitution, you will get to 17.33 ohms. Cos phi is R by Z. From this, the resistance value is obtained to be 11.26 ohms. The reactance is nothing but Z sin phi, and here in this case we have obtained 13.17 ohms. After including capacitor, the resistance value will remain same, but the reactance value will change. Here also, since one of the wattmeters will become 0, because there is the condition that the whole of the power should appear only on single wattmeter, which indicates the phase angle to be 60 degrees. The new reactance value we assume to be x dash, and that can be calculated by using tan phi is equal to x by r, which will give me the new reactance value to be 19.5 ohms. From this, if I subtract the old value and new value, will give me the capacitive reactance to be 6.33. From that, the capacitor that should be introduced in each phase value is 502.86 microfarads. So this concludes my today's lecture on the concept of three-phase power measurement using 2 wattmeter method. Thank you.